I thought we'd start with a little bit of fun here, since ICHEP is starting to have results. Started yesterday. So I thought, just for fun, here are the H goes to gamma gamma results. And you can see that the 750 GeV resonance is gone. These are CMS results. We don't have the Atlas results. And what you see here, well, okay, here we go. No, I can't do that. Okay, 750, that blue dip, that's what we had last year that got 300 theory papers written, right? So the black is now, what's that? So the black is now the combination of last year. I don't know. My pointer. Okay, so that's last year. That's 300 theory papers. Okay, this is 3 sigma, so it's 2.9. So here we go. Here we are right now. It's less than 2 sigma. But the interesting thing here is that you see lots of bumps. You know, statistically, you're always going to see lots of bumps. So here's one at 650. Okay, so here we are, 2 sigma. I predict some papers. Here we are up at about 1.2 TeV, another 2 sigma bump. So, okay, there's physics there. We've also started to see ICHEP results are starting to come in on stuff like gluinos. The gluino limit is now up to about 1.9 TeV. So, for fun, all right, there we go. Yes, there. Okay. So, for Higgs physics, what that says to me is that the standard model is a pretty good approximation. So all this stuff on effective field theories as the way to look for new physics is something we really have to take seriously. Because if there's any new physics up there, it's likely to be, you know, at a pretty high energy scale. So, all right, so today I want to finish my spiel on low energy theorems and effective field theories, and then hopefully I'll have time, I'll make time, to go through glue goes to Higgs, goes to ZZ as a case study for how you might measure the Higgs width. All right, so low energy theorems. These are kind of nifty. So, suppose you're calculating the coupling of the Higgs to some heavy fermion, and it's in the center of some complicated Feynman diagram. I don't care what's going on in this Feynman diagram. So I'm just calculating this thing. So this is a K. Here's pH. So this Feynman diagram, sorry Nima, I love Feynman diagrams. I over K minus M minus I M over V 1 over K minus M, K minus pH minus M, and then what, okay. So that's what you get just from this subdiagram. So it's easy enough to see that as pH goes to 0, i.e. the mass of the Higgs is much, much less than the mass of the top, this goes to the same stuff, whatever it is, I M over V, 1 over K slash minus M squared times the same stuff, okay? So this thing is the same stuff, I M over V, d by dm of 1 over K slash minus M times the same stuff. So adding a Higgs to any diagram is the same as just taking the derivative with respect to the mass. And the Russians formalized this to a theorem, so low energy theorem. When people say that, what they mean is that the limit pH goes to 0, pH goes to 0, of any amplitude with a Higgs plus whatever, doesn't matter whatever, is M over V d by dm times the amplitude without the Higgs. Okay, it's low energy theorem. And this has been used to calculate all sorts of radiative corrections, higher processes. The only sort of subtlety here is that this is the unrenormalized mass. So that if you use this thing for higher order corrections, you actually get terms which depend on the renormalization of the mass which come in. Okay? So there we go. It's a low energy theorem. So let's just apply this to the gluon 2-point function. Okay. So L equals minus 1 over 4 GS squared G mu nu A, G mu nu A, where I'm going to write the gluon with all the scale pulled out. So G mu nu equals d mu G mu nu minus d nu d G mu A, get my sign right here, plus F A B C G mu B G mu C. This is the way the lattice guys like to write this. I noticed Nima normalized it this way too yesterday. So you redefine your gluon fields from the usual way so that there's no G here. So all the scale dependence is pulled out front. So then if you apply the low energy theorems, what do you get? L equals minus a quarter H over V d by dm 1 over gs squared md by dm g mu nu g mu nu. Okay, so anybody know what the mass derivative of the gauge coupling is? Keep going. What if I used a different notation for my mass scale? What if I called it mu? Mu d by d mu of the coupling? It's a beta function. Right, it's the beta function. Awesome, huh? So this thing is just, I just get 1/4 times 2h over v times beta over g, g mu nu squared. And I'll put a t here because it's only the heavy fermion contributions to the beta function that are relevant. Okay? So this thing is actually alpha s over 6 pi. So this works no matter what's in this loop. So you can have heavy color octets, you can have squarks, it works for squarks, it works for anything. So there you go. The low energy theorem tells you that the coupling of the Higgs to gluons is really just the beta function. Okay. So this is extremely useful, this effective theory. I guess I should write, I'll write the answer here, alpha s over 12 pi v h g mu nu a g mu nu a. So this is how we calculate radiative corrections, and it works extremely well. Glue, glue goes to H. So one loop, you get this kind of stuff. So why do you think it might work so well for the Higgs mass, or for the radiative corrections to Higgs production? This is physics, actually. It's an expansion in powers of mh squared. It's actually, you get a 4mt squared downstairs. But there's only one scale here, right? There's only the Higgs mass and the top mass. So there's one ratio. That's all you got, right? So numerically, this is actually, less than 1. So it works extremely well when I calculate radiative corrections to this. Okay, so now I try to play the same game. I'm really interested in maybe Higgs plus 1 jet. Okay, so Higgs plus 1 jet, been calculated a long time ago. Here's a top quark box. I can do the same game and calculate it in the effective theory, right? So here we have jet Higgs. Okay, but now when I calculate in the effective theory, I've got more scales. I've got kinematic scales, ST and U, say. So I've got S over MT squared, T over MT squared. That's it. So that's one of the themes, I think, of this school is unitarity. Nima pointed out that unitarity conservation was really important for getting amplitudes. I was emphasizing that effective field theories don't work so well when you approach high energy. And again, this effective field theory, here you go, S over mt squared, at some point you're going to get big contributions and it won't work very well. And in point of fact, when you try to use this kind of effective field theory to get distributions, maybe you're interested in d sigma, dpt of the Higgs, you're interested in the some invariant mass, it doesn't work very well. It gets the shape of the distributions wrong. It gets the overall cross-section sort of right, but it doesn't get the shapes of the distributions right. But in some cases, this effective field theory is all we have. I mean, this is a nice example here because we can calculate exactly in an effective field theory. But if I'm trying just to use the effective field theory, I'm going to get terms like this and my distributions, they just don't come out right. But nonetheless, it's extremely useful. Good. So let me just show you something that I think is extremely cute before I go on. And this is for the model builders in the room. Okay. So I started with a Lagrangian, which maybe had a lot of fermions. Well, let's just call it F bar I Y I H plus V F I. So in a mass basis, my Yukawa couplings are diagonal and they're proportional to the mass. So these Yukawa couplings are just the mass over V. Okay, this is a standard model. But now you guys have built some complicated model, composite Higgs, heavy fermions, vector-like quarks, whatever it is. You got some complicated model, and you got a bunch of heavy states, and it's typically a boatload of work to diagonalize the mass matrix to find the Higgs coupling, especially you got a lot of stuff. You know how to do it, but it's actually kind of a lot of work. So there's a trick. All right. So what I really need is I need this combination yi over mi. Right? So I need this combination to find, did I erase it? To find the Higgs coupling. So this is just 1 over V if I have the top quark. But if I have a whole bunch of fermions, this is the combination that couples to gluons. Okay. So suppose I've got my more complicated model. Let's call it Yij tilde. Okay, so I build my model. I write down the couplings to fermions, Ij. They're not diagonal in general. I've got some big complicated mass matrix. Okay, so I need the couplings to the Higgs. Okay, so I can take this guy, and I can diagonalize things in the usual way with unitary matrices. So this goes to F bar. Which order did I write here? U dagger Y tilde U dagger F times H plus V. Okay? In the usual way. So the diagonal mass matrix is just MD. I've got a V equals V U dagger Y tilde U. Okay. So I diagonalize things in my usual way. And so now you can guess that you can play around with properties of unitary matrices here, right? Okay. So this guy is the sum over I U dagger non-diagonal mass matrix U over M. This is diagonal. So this guy is the sum. Well, now it's going to be the trace, since I've got matrices. U dagger Y tilde U. M diagonal minus 1. Okay, so this is all super easy. But now you can play around with your properties of unitary matrices. and in particular m minus 1 m, so these guys are the non-diagonal guys, equals m minus 1 u m diagonal u dagger equals the unit matrix. Okay, so there, all right. So you play around with this, put things in, and work it out. And the coupling to the Higgs is now the trace of the non-diagonal Yukawas, the non-diagonal mass. Okay, so now I got the couplings of the Higgs in terms of the stuff I wrote down when I wrote my model, which is extremely useful. Okay, so now if you play with your matrix identities, and these are not so obvious, by the way. It took me a long time to check this. Trace log of m. Okay. Let me just... So in my complicated model, with my complicated mass matrix, I can just get the couplings of the Higgs in terms of the trace log of the mass matrix. Well, that's kind of nice. So now, in the high energy limit, I don't need to diagonalize mass matrices. And this is extremely useful. So in general, the Lagrangian is alpha s over 12 pi d by dv of the trace log m h g mu nu g mu nu. All right. So the composite Higgs people use this a lot because, like I said, who wants to diagonalize a mass matrix? It's a lot of work, right? So where might this be valid? This is valid in the limit that all the new fermions, m nu, all this new junk, is much, much greater than m Higgs. And we actually know that that's a pretty good approximation. I mean, look at the ICHEP results. I'll bet there are going to be all sorts of new limits on heavy fermions, heavy stuff. We know that heavy stuff is heavy, is much heavier than the Higgs mass. Okay, so that's cool. Anyways, I have all the details going from here to here in my notes just because I had fun working out how it goes. And like I said, it's not so obvious how it goes. All right, so you build yourself a model, and you can calculate the couplings to the Higgs without doing any work. Always a plus in my mind. Okay, are there questions? Because now I'm going to turn to the Higgs width. Anybody? And if you have trouble with the matrix identities, if you Google them on Wikipedia, you can find them worked out. Although maybe you all know more matrix identities than me. All right, so the Higgs width. How do I get the Higgs width in the standard model? In the standard model, I would say gamma h is just the sum over gamma I over standard model decays. So I just add up the width to everything that it's allowed to decay to. Most of the time, the Higgs wants to decay to B's because they're the heaviest thing around. So that's the biggest contribution. But then there are contributions from W plus virtual W and so forth and so on. So you add them all up. And it's equal to 4 MeV. You'll remember, everybody remembers these numbers from Maxime's lectures, that the width of the Z is about 2 GeV. The units are different, okay? So here it's 4 MeV. So Maxime was talking about looking for the Z boson and measuring its width by looking at the width of the resonance. So let's see if we can do the same thing at the LHC. We're going to look for Higgs to gamma gamma. Nice clean signal, nice bump. There are lots and lots of gamma gammas which just come from QQ bar goes to gamma gamma. So it's gamma, gamma, Q, Q bar. Okay. So what we'll do is we'll look for D sigma, dm, gamma gamma, m gamma gamma. So the background, the uninteresting stuff, has fallen like a rock. This is a logarithmic scale with many orders of magnitude. And the Higgs bump is just little bitty bump, okay? So the experimentalists, instead of trusting us theorists that we actually might have known how to calculate gamma gamma, they do a fit to the background on either side, a polynomial fit, and then they just subtract it. So they subtract the background and then they see a bump. Okay, that's how it works. Okay. The problem with measuring the Higgs width this way is that the experimental resolution is 1 to 2 GeV, and the Higgs width is 4 MeV. So you can't just measure the width here of this thing, because what you're really seeing is the detector resolution, not the intrinsic resolution of the Higgs. So for a long time, we just said, we don't know how to measure the width of the Higgs. Okay. But then Nick Kauer, Kirill Melnikov, Fabrizio Caoli, they had this really clever idea. And this clever idea depends on the properties of the Higgs boson. That's why it's so clever. And you can understand it using simple physics arguments. So let's go back to my favorite process. Glue goes to Higgs. So we got glue. It's going to go to a Higgs. I'll just put a blob there, but in fact, I calculate it with all the effects there. Goes to 2 Z's. Z, Z. So this is a nice clean signal. In fact, it's just been reobserved at 13 TeV at the LHC. When you look for the Z's, they each go to 2 leptons. You reconstruct the invariant mass of the 4 leptons, and you get a nice bump at the Higgs. Okay, so you can remember that Maxime talked about PP goes to Z, goes to, say, E plus E minus, and you get a nice bump like this. So that's what we want to do with this, to see if we can use the same kind of techniques to measure the Higgs. Okay, so let's just assume there's some scaling factor here, which we'll call kappa G. And here, there's some scaling factor here, which we call kappa Z. So we'll just let the standard model interactions float with some arbitrary scaling. So then the cross-section for this process, sigma is going to be on the integral over some final state momentum of these 2 Z's times, I'll put a hat here for a reason I'll explain in a minute. GG goes to H, goes to Z, EZ squared over S minus MH squared plus gamma H squared MH squared. I put the hat on there because I've explicitly pulled out the propagator of the Higgs here. I want to think about that separately. Okay, so here's an amplitude. Okay, all right. So now, let me see here. How am I going to do this? I want to make sure I don't erase things. Let me go back over here. Let's think about the properties of this amplitude. So let me go to an energy S much, much greater than mz. So I'm going to go to the high energy limit of this amplitude. Okay, so what's the amplitude going to look like? So the amplitude, GG, goes to H, goes to ZZ, is going to look like, and I'm not going to put down all the factors of 2's and pi's and so forth, and this drove the TASI students nuts for some reason, but it's just too distracting to write down all the factors. So the amplitude is going to have a factor of kappa G here, a factor of kappa Z here, okay, for my rescaling. It's going to be kappa G, kappa Z times epsilon of PZ1 dotted into epsilon of PZ2, okay? The HZZ vertex, remember, is just G mu nu. So it's epsilon of this guy dotted into epsilon of that guy. Okay, so are these epsilons? Okay, so the transverse polarizations, Nima wrote them down, yeah? 0, 1, plus or minus I, 0 with a 1 over square root of 2. So the transverse guys are completely uninteresting. You do this dot product and you get 1s and 2s, right? Nothing interesting at all. However, remember at high energy, you guys all remember longitudinal polarizations, that's where it's at, right? That's where the interesting physics is at. So the longitudinal polarizations at high energy go to P mu over mz. Yeah? So when I take the dot product of those two polarization vectors, pz1 dot pz2, what do I get? Nah, I'm not on the resonance. I'm far above the resonance by assumption. I get S, right, with some factors. Okay? So this thing just turns into S over mz squared. I'm looking at the above the resonance. I'm not on the resonance. Okay, so this is kind of cool. Let's see what happens to the cross section above the resonance. Mz squared, yeah. Okay, and this is what drove the TASI kids nuts, because they remembered in their hearts that 2-to-2 processes are dimensionless, and then when I'm going to go on, my units aren't going to be right because I didn't put in all the factors. But believe me, I put in all the factors that scale with S, which is the only thing relevant. Okay, so sigma, we'll call it above. So sigma above the resonance, S much greater than mz squared. I'm going to get kappa g squared, kappa z squared. Okay, S squared. Well, I'll skip the, I'll put it in. Over mz to the 4th. There we go. And over here, I'm far above the resonance, so I only pick up this term, right, by assumption. So I only pick up the S squared term above the resonance. Yeah? Over S squared. So it goes to something which is kappa g squared, kappa z squared, times some other stuff. So sigma above goes like kappa g squared, kappa z squared, times stuff. So this is really different than what happened in the z case over here. So let's make this pp goes to h goes to zz. Above the resonance, it doesn't go like the z resonance, but I get this tail out here. So it looks really different. And in fact, at the LHC, at 8 TeV, roughly 15% of sigma is greater than m4 lepton equals 140 GeV. So there are actually events out here, okay? And those events are just because of the longitudinal z's. So there's real physics here. So you don't have to be a rocket scientist to do this, which is why we were all mad we didn't do it. Okay, so that's very fine. Now let's go back and see what happens when I'm on the resonance. So I'll keep my box, well, let me write my box over here. Sigma above. It's on the order of kappa g squared, kappa z squared. All right. Now let's go back and go sigma resonance. So now let's look at what happens when S is roughly mh squared. So 1 over S minus mh squared plus mh squared gamma h squared goes to pi over gamma h mh delta of s minus mh squared. This is the narrow width approximation. So how many of you guys have derived the narrow width approximation? All right, 3 or 4. I'm not going to do it right now because then I wouldn't finish, but maybe I'll put it in an appendix in my notes because it's actually kind of fun to derive this. But this is a narrow width approximation. It's the same thing that we used, Maxime used it when he was thinking about LEP data. I'm going to use it here. Okay, so what does that tell me about the cross-section on the resonance? Sigma res. Well, I'm still going to have these kappa factors, right? Kappa g squared, kappa z squared. But now I'm going to have a 1 over gamma h from the narrow width approximation over gamma h. Well, okay, this is kind of interesting. So now I'm just going to take the ratio. I'm going to take sigma above, so sigma high energy over sigma resonance, and it's going to depend on the width. Okay, so the idea is that you're going to measure the Higgs cross-section on the resonance, which is exactly what they did at the LHC. Then you're going to take the same data to ZZ, put this cut on, and look up here, and that piece will be sigma above, and there'll be a dependence on the width. Is that cool or what? That's like cool. Yeah, really. Okay, so there are a few fallacies in what I've done here. Anybody want to tell me the first thing I've done that's sloppy and not right?
Rescaling the coupling.
What's that?
Rescaling the coupling.
I'm coming to that one. That's true, but that's not what I'm fishing for right now. Interference. I can't just pick out this term. Come on, guys. Quantum field theory doesn't work that way. I'm swindling you, right? So let me write sigma res is on the order of kappa g squared, kappa z squared over gamma h. Okay, we all know how to do quantum field theory. Carol's no dummy. He knows how to do this right. So I actually have to calculate glue. Here's a box with light fermions. It doesn't just have to be the top quark. Goes to Z fermions. And there are a bunch of diagrams that contribute to glue goes to Z that have nothing whatsoever to do with the Higgs. Plus, and then here's my signal. Glue, top, H, Z. So I actually have to calculate the whole thing and square it, okay? And that, of course, is what people have done. So it kind of washes this out, right? Because you have sigma, so then sigma goes like, let's call this stuff B. Goes like sigma B, the stuff I'm not interested in, plus sigma interference, okay, the interference of these two things, plus sigma, I'll call it S, okay. So you got to calculate the whole thing, and it somewhat washes out this effect, but this effect actually remains even after you do this, okay? So you can still get interesting limits on the Higgs width. And in fact, the experimentalists have done this, and they get gamma H is less than or equal to 4 to 5 times gamma standard model. So, okay. This is pretty cool, huh? So you thought you couldn't get a limit on the width, then you actually get that is 4 to 5 times the standard model. So the less than about 20 MeV, okay? And that's, of course, interesting because my prediction for gamma H is equal to 4 MeV assumed all I had was a standard model. But in principle, you could have the Higgs decaying to a bunch of invisible things, right? Dark matter, axions, whatever your favorite model had. It's not guaranteed that the width of the Higgs is a standard model prediction. There could be a bunch of invisible stuff. Okay, so by measuring it, you want to actually see what the width to this invisible stuff is. Anybody have an idea why it's 4 to 5 there? Yeah? Well, it's because these are gluons in the initial state. And one of the points I made is that when you have gluons in the initial state, you always got big radiative corrections. It just always works out that way. Alpha S isn't that small. You always get big radiative corrections. So the 4 to 5 depends on some estimates of what the higher order corrections are to this guy. These guys are actually calculated now, so we can actually reduce that 4 to 5. But the experimental analysis just put in some models for how big they thought the corrections might be. Okay? So, all right. So now you pointed out the other swindle of this thing. Any questions? Yeah? Okay. So that was one swindle. You needed the interference, but I claim it still works, and it's because of these longitudinal guys. But when I did this, I assumed that these kappas were just constants. Well, we all know that in a quantum field theory, everything scales, right? So these guys, these kappas here above, are really kappa g of s squared kappa z of s squared. And these guys on the resonance are really kappa g of mh squared kappa z of mh. Let's see, let's erase this. Squared, okay, and over gamma h. So these kappas really scale. So if I have some model where there's some physics coming in between the two scales, between S and MH, they won't be the same. And in fact, there's a whole industry of people who've constructed models where these kappas scale. So that's an assumption here, that there's nothing really making these kappas be much different. Okay? There's one more assumption that comes into these things, and that's that there are no effective field theory contributions coming in, or that the effective field theory contributions are small. So L standard model plus some C over lambda squared times a bunch of operators. I've written this down before. So there are a number of operators which could affect the coupling of the Higgs to the Z. I'll just give you one. Z mu nu, Z mu nu. Okay? This operator is going to generate S over lambda squared contributions to this thing, the way EFT operators always do. So what happens is that d sigma dm 4 leptons, here's m 4 leptons, instead of going off to be kind of flat there, it's going to go like that, EFTs. All right? So if you have EFTs, this whole interpretation of this as the width kind of falls apart unless you make these EFTs really small. Because of course you put this in by hand. So, okay? Any questions? Yeah.
The experiment, how to define sigma above and sigma resonance?
Oh, that's easy. That's a great question. Okay. On the resonance, all right. Okay, so this will go to, say, E plus, E minus, and this guy will go to E plus, E minus, 4 leptons. So they take these 2 leptons, and they have to have an invariant mass of the Z. And these two leptons have to have the invariant mass of the Z. So for on resonance, the 4-lepton mass has to be the Higgs mass, right? But they measure the invariant mass of the 4 leptons. So they just put a cut here that, say, M4 lepton is greater than, I don't know, 140 GeV. Some number, they pick a number. So they just put a cut on their 4-lepton signal. So they don't separate out the Higgs signal. They just look at their sample where they have 4 leptons, of which 2 come from a Z and 2 come from a Z, and put a cut on it. So it's a physical thing.
So what about the resonance? You need to cut out some beam, right?
Right, so you have two samples, right? So you have a sample where you put a cut on the 4-lepton mass that it's big, and then you put a cut on the 4-lepton mass that it's within some window around the Higgs. Yeah. So the one sample is just their Higgs sample that we know and love. Yeah? Yes?
Shouldn't one see the contribution from the EFT on
Yeah.
the distribution? So
Yes.
you could actually tell how good this approximation is, more or less.
Well, no, you would make a limit on the EFT coefficients, right? So you,
I mean, if the cross section was rising again,
yeah,
then you would probably not. You would know that.
you would know that you'd have an EFT, right? So you wouldn't say I'm measuring the Higgs width. You'd say there's some EFT coming in. That, of course, is exaggerated, right? Because it depends on C over lambda squared. I mean, in the real world, it's probably more like that, or I mean, it depends on how big you make it. Yeah. So, but yeah, that would be cool too. Yeah. Rise and cross sections are always neat because they're always a signal of effective field theories coming in, something happening. You know, that was the same thing when I talked about 4W production. If you see rise and cross sections, you violate unitarity and something's going on. Okay. Any more questions? Okay. I'm predicting we'll see this week some more limits on this. And I'll bet they'll be better, just because we'll have 8 TeV data. Okay. All right. Okay. So measuring the Higgs at the LHC, the Higgs width at the LHC, turns out to be not completely impossible, right? Okay. But there are all these assumptions there. So this led people to think, E plus E minus machines, they're way better. Actually, I might as well turn the board over while I'm at it. Okay. So I still want to know what the Higgs width is, and I want to know it without any of these nasty assumptions that I have to make at the LHC. Well, at an E plus E minus collider, it's, you know, like the first thing you do. Yeah? So E plus E minus goes to Z, goes to ZH. Okay? But you know one thing at an E plus E minus collider that you didn't know at the Hadron Collider, because you know the initial state energy of the E plus and E minus. At the LHC, you got to integrate over the PDF, so there's a spectrum of momentum. But at an E plus E minus collider, you just know these guys. So you can measure, let's call this P1, P2, P3, pH. So pH is equal to P1 plus P2 minus P3 squared, pH squared. So pH squared, of course, is the mass of the Higgs squared. So you know P1 and P2, they're just square root of S over 2. They're fixed. So you measure the Z decays to, I don't know, let's call it L plus L minus, I don't care. So you measure the decays to L plus L minus, and you reconstruct this invariant mass of these guys, where the L plus L minus invariant mass tells you that you got a Z, because you pull it out. So this quantity fixes Higgs events, right? Because we know the Higgs mass, so you fix Higgs events. Okay. So we know sigma ZH, measured pretty cleanly. Okay, so now that you got a sample of events that you know are z plus h, then you look for h goes to z, and then you measure the branching ratio of h goes to zz. Because you know your events have a Higgs, and then you just look at ZZs here. You let these guys go to 4 leptons or whatever, reconstruct the Z masses, reconstruct the Higgs masses, so you know the branching ratio H goes to ZZ. Okay, but now you note that this ZZH vertex is exactly the same as this HZZ vertex. Okay, it's the same coupling there. So you can, gamma H is equal to gamma H goes to ZZ over the branching ratio H goes to ZZ. And this thing here is proportional to sigma ZH over the branching ratio H goes to ZZ. Okay, so you take your sigma ZH and you extract gamma H goes to ZZ because it's the same couplings and all, and you get a measurement of the width. And in fact, at a 500 GeV E plus E minus, let me get my numbers right, with 500 inverse femtobarns, you get 5% on gamma H. Okay. And the E plus E minus aficionados really love this because there are no messy assumptions. So it's a model-independent measurement of gamma H. Okay? And then you can use this to get measurements of the Higgs couplings, which are in the 1 to 2% regime, whereas the LHC is never going to do better than about the 5% range, no matter how much they have. So it's nice and clean. So this is one of the motivations for E plus E minus machines. Okay. Are there questions? No? Okay. Good. All right. Well, I didn't mean good there were no questions. I just meant good that maybe you understood what I was saying. Okay. So let's go back to glue goes to H, my favorite process here. All right. So there's one thing I didn't talk about measuring, and it's really important. Okay, we started out, we had this potential V equals mu squared phi dagger phi plus lambda phi dagger phi squared, which is equal to mh squared over 2h squared plus mh squared over 2vh cubed plus mh squared over 8v squared h to the 4th. Okay. And we also know that these things here are relatively small numbers. If I call this lambda 3, then v times lambda, let's see, yeah, v times lambda 3 over v, I want to make it dimensionless, over v is 0.13. So everything is nicely behaved. There are no big couplings or anything. But on the other hand, if I'm in a model with 2 Higgs doublet supersymmetry or something, these lambda 3s will be different. If I'm in a composite Higgs model, I won't have this structure at all. I'd really like to know if the Higgs mechanism has anything to do with the world, right? Because I haven't actually measured that the Higgs and its couplings come from this scalar potential. So I really, really want to measure this guy. So there's only one way to measure the Higgs trilinear coupling, and that's you got to make two Higgses, okay? So the largest rate for measuring the trilinear coupling comes from double Higgs production. This is predominantly a top quark. Top H so if I could measure this rate, I could actually get a limit on lambda 3. Well, there's one problem here, and the problem is you're making two heavy guys, two Higgses, and you've got top quarks in the loop, so the rate is actually extremely small. So sigma 13 TeV is equal to 34 femtobarns. Okay, and then you got to put some branching ratios for these guys to decay to things that you can actually see. Sigma 100 TeV, let me get my numbers right, is equal to 1760 femtobarns. So this is actually one of the strong motivations for building a 100 TeV collider, is that you're actually going to make this double Higgs production with a fairly large rate. However, you got a problem here when you're trying to use this to measure double Higgs production. Okay, so the rate here, the amplitude, glue goes to H. H is going to have a something times a spin 0 piece. Here's spin 0. Plus something times a spin 2 piece. Since you've got two gluons, you can actually make a spin 2 piece. Okay. If I go to the MT goes to infinity limit, which is my favorite limit you guys gathered, this guy goes like PT squared over MT squared. Most of the cross-section is at low PT, so most of the cross-section is a spin 0 contribution. Okay. So this spin 0 contribution okay, let me write down, is some numbers. 1 minus lambda 3 V over S minus MH squared, P0. Okay. So the spin 0 contribution here has a piece from the box where I've just pulled it out, and a piece which is actually proportional to the thing that I'm interested in, lambda 3. So you see that there's a big cancellation here. So when S is equal to 4 MH squared, this thing actually vanishes. So I can write this guy as 3 MH squared times delta lambda 3 over lambda 3 standard model. Let me write it that way. So at threshold, S equals 4 MH squared, okay, this vanishes. So the dependence on lambda 3 is smaller than you might have naively thought. Okay, so you got a small rate, and you got this cancellation here at threshold in the spin 0 piece. And all of this combines to mean that you can't measure it very well, which is unfortunate. So at the LHC, with 3,000 inverse femtobarns, so this is the plan that takes us to 2037, I think, maybe 2035, way in the future. Atlas says, they're going to have, hold your breath, guys, 2 sigma observation. Ooh, that's cruel, right? That's really cruel. So this is why, since you're young, a 100 TeV machine might be interesting, because this is going to be pretty hard at the LHC, right? 2 sigma in 20 years? I mean, experimentalists always get smarter as time goes on, but they don't have a lot to play with. So with this 2 sigma observation, they can delta lambda 3 over lambda 3 standard model, the deviation, they're sensitive to this guy greater than 8.7 or less than minus 1.3. Okay? So it's not going to be a precision measurement of the coupling to the Higgs, unfortunately, the trilinear coupling. So that's the glass half full approach to this. Now let me put on my, well, that's glass half empty, I guess. That's a negative approach. But there's something really positive about this also. So since the standard model is so hard, and it's a counting experiment looking for this, that opens the road to new physics. Before I go on, I shouldn't forget to say that the current limit on double Higgs observation is sigma over sigma standard model. Sigma HH is less than 70. So it's not that there's no limit. It's just that it's not a particularly interesting limit. Okay. Anybody? But okay. That has its good points because that means that double Higgs production is exquisitely sensitive to new physics. In particular, it's sensitive to new resonances. So I have my standard model contribution here. But if I have some model, say the 2 Higgs doublet model, the MSSM, the Higgs singlet model, any model with a Higgs singlet, you're likely to have new contributions. Goes to some heavy resonance, goes to H. And the experiments have looked for heavy resonant effects in double Higgs production, and it's interesting that the best limit is actually from the Higgs goes to 4Bs. So they get limits that depend on the mass of this guy, which are not so far from the standard model, 10 to 20 times the standard model for some of the Higgs masses. So as a theorist, you say, well, I want to calculate sigma GG goes to H, standard model H. And I want to see how big I can make double Higgs production, right? You want to see just how big this thing can be. So you got the singlet model, you got the MSSM, you got 2 Higgs doublet models, and you play around with all your parameters to make sure that things aren't ruled out. And the biggest numbers that anybody's been able to get are sort of 10 to 20. So you can't really get enhancements of 100. You can get 10, you can get 20. The MSSM people got 50 a few years back, but then it turned out that a lot of those points were excluded. So you can enhance double Higgs production, but the rate is still, pretty small at the LHC. Okay. Questions? Okay. All right. So double Higgs production is actually interesting for the effective field theory people too. Okay, and the effective field theory people, so they're calculating stuff like this. And they say, well, maybe there's some new vertex here which changes the coupling of the top quark to the Higgs. Maybe there's some new vertex here, H, CG, which changes the effective coupling of the gluons to the Higgs. Remember I told you that sigma GG goes to H was only sensitive to the CT plus CG squared. It couldn't distinguish between these two new effects. But now when I'm doing double Higgs production, I got more stuff. So I've got corrections which depend on CT here. I got stuff H. This guy is related to this guy if I assume that the Higgs just comes from an SU2 doublet, because I have G mu nu, CG, alpha S over some pi, depending on my normalization. This is the effective Lagrangian that I was developing before. But if I'm going to build a field theory where the Higgs comes from a doublet, I'll put in phi dagger phi. Okay? If I expand phi dagger phi, H plus V squared, the coupling to a single Higgs and the coupling to a double Higgs are related to each other. Okay? So I'm going to try to see if I can learn anything about EFT coefficients from double Higgs production. And now it's interesting because these things have different kinematic dependencies. Just like I went through the kinematic dependencies for glue goes to H goes to Z, looking at different regimes, this guy is going to have a 1 over S. This guy is going to just be a constant. Okay, so they're all going to have different kinematic dependencies on these coefficients. And it's not so hard to show that by looking at the invariant mass, say, of the two Higgses or the rapidity distribution, you can actually now separate out the effects of these guys. Okay? Questions? Okay, because I'm going to turn to one more thing before I stop, and it's completely different. So if you have questions about this, you should ask. Okay. All right. So I erased it. I always erase the things I want. All right. So double Higgs production is trying to understand the structure of the Higgs potential. So let's go back to the Higgs potential and think a little bit more about it. So let's just V of phi equals m squared over 2 phi squared plus lambda over 4 phi to the 4th. So I'll just think about a scalar phi to the 4th theory for now. Okay, so this is supposed to be the standard model, where in this normalization it's correct to have lambda equals mh squared over 2v squared. Okay, well, in quantum field theory, we know what happens to couplings, right? They run. So this lambda, these guys are at the electroweak scale. So we want to ask what happens to our theory as we take these lambdas and try to run them up as high as we feel like, the Planck scale, whatever. And you heard actually a student talk on this subject. So a much more sophisticated version than this. The point is that I can calculate the running of these lambdas in a well-defined way. Right? And how do I calculate this? Well, let's consider H goes to H scattering. Well, actually, I should call it phi, right? Since I'm calling them phi's here. Doesn't matter. Okay. So I'm in a theory with only scalars. And I want to calculate how this lambda runs with energy. So what do I have to calculate? Well, there's this guy, where these guys are all these phi. There's a T channel. And then there's a U channel. Let's see if I can draw it. It goes kind of like, oh, that's not so bad. Okay, so I got to calculate these guys. It's phi 4th theory, so we know how to calculate it. It's not too hard. And since I want to calculate the running of lambda, I remember I remember that I'm lazy and I don't want to calculate anything too hard here. That when I calculate these loop diagrams, I get factors of, in dimensional regular, 4 pi mu squared over, say, mu naught squared to the epsilon 1 over epsilon, which gives me my log mu squared over mu naught squareds. So the logarithms from the running are always associated with the poles, the 1 over epsilon poles in dimensional regularization. So that means that I only have to calculate the pole contributions to these diagrams if I'm going to do it in this order. So it's not so hard, right? You calculate these diagrams and you get the poles. Okay, and so when I calculate these diagrams, what do I get? I get the amplitude is equal to minus 6 lambda. So that's the tree level, this guy. Hopefully I got my combinatorics right. 1 plus 9 lambda over 16 pi squared times the log, what did I call it there? Mu squared, and I'll take mu naught squared to be mh squared. Doesn't matter. Some electroweak scale. Okay? Plus blah, 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 blah. Huh? Okay. So this tells me that lambda runs with mu squared. And I can just define this to be minus 6 lambda of mu squared at lowest order. Well, there's a problem with this. Anybody see what the problem is? Okay, nobody sees what the problem is. So what happens when I take mu goes to infinity? I want to take this theory as being valid all the way up to the Planck scale. So it says that no matter how small a lambda I start out with, it eventually blows up, right? I start out with lambda super small. Well, that just puts off where it blows up. So this is a general problem of this theory when you try to make it valid all the way up to the Planck scale, right? Okay. So the theory is not quite consistent. There's another problem with the theory. Okay. Which has to do with the same idea, the running of lambda. Okay, so I started out with this potential V of phi at the electroweak scale. Looks like this. Okay, we said that this was a nice potential when lambda was positive. But what if when I run, okay, so let's go up to high scale. What happens if lambda goes negative, lambda less than 0? It's unbounded. So I can't let that happen either, because then my theory wouldn't make sense. And in fact, people have now calculated what happens when I try to go to the Planck scale. And let me get my numbers right. It's done to 3 loops. So here's the quartic coupling of the standard model at the Planck scale as a function of mu. Okay, and it goes negative. All right, here's 0. It goes negative just below the Planck scale. And it's exquisitely sensitive to the top quark mass, because the top quark is the biggest coupling, so it drives it negative. If you want to have lambda, let's say at m Planck equals 0, so it doesn't go negative before you get to m Planck, you've got to have the Higgs mass less than 129 GeV. So our world is very close to a world where the standard model could be valid all the way up to the Planck scale, but not quite. Okay, so. All right, questions? These are sort of motivations for new physics, because you can change all these arguments, of course, by putting new physics in. All right. So the standard model isn't perfect, and there's one more thing that's not perfect about the standard model. And that's when I calculate the Higgs renormalization.
Sorry?
Yeah.
So is Higgs mass, or maybe it should be top mass? You just mentioned that it's sensitive to the top mass?
This is exquisitely sensitive to the top mass. And this calculation, m top is 173, but if you had changed the top mass to be 180 or 60.
But you had like MH.
Oh, I meant MH. I meant MH. I meant that, well,
Like what did you mean then?
oh, if MH is, yeah,
It's a bit confused.
yeah, I did mean MH there. Let's see here. I did mean MH. I meant that M Planck is greater than 0 up to the Planck scale if MH is less than 129 GeV.
But then you said that it's not quite, but we have 125.
Right, and it's close, right? I mean, yeah.
Shouldn't be greater than.
Do I mean, do I have the sign wrong?
Maybe sign.
No, I mean, it is a less than. Yeah. Let me triple check my numbers later. Okay. But,
Because this is our.
yeah, our world. Yeah, but the reason I didn't bring the plot, and this band depends on MT. Yeah. Yes?
How can you measure the running of the lambda? Because
Oh, you can't measure it. It's completely theoretical.
exactly.
It's theoretical. Yeah, so maybe there's some more stuff there. These are theoretical things. Yeah. So you don't measure it, right? It's theoretical. Yeah. All right. So finally, the other thing that makes people unhappy about the standard model is the Higgs renormalization. So suppose I start from a Lagrangian. L equals psi bar I d slash psi minus lambda f psi bar left phi tilde psi right. So this is, say, the top quark plus Hermitian conjugate. Okay? And suppose I first calculate the renormalization of this fermion here. Okay? So I'm going to calculate, this is an electron, this is a top quark, this is any old thing you want. So here we go. Fermion, 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 Higgs. So this guy is going to be proportional to lambda f squared, the Yukawa coupling squared, lambda f squared. And if I do it in 4D with a cutoff, cut off lambda, this thing is going to, the factor is minus 3 over 64 pi squared times the log lambda squared over the mass of the fermion squared. But of course, this Yukawa is essentially the mass of the fermion, right? The Yukawa coupling is the mass of the fermion. Okay? So this goes like the mass of the fermion over V squared times the log of the lambda squared. So how did I know it had to be this way? I could have guessed this before I started. What's that? Yes, exactly. It's because there's a symmetry here. I could have written the Lagrangian as L equals psi bar left d slash psi left plus psi bar right d slash psi right. So when I take the mass of the fermion goes to 0, there's a symmetry. So taking the mass of the fermion to 0 increases the symmetry of the theory. So you get this thing vanishes as the mass of the fermion goes to 0, and it's just a log dependence. And logs vary kind of slowly. Okay? So now let's do the same calculation with a Higgs. Exactly the same Lagrangian. And in my notes, actually, I worked out how to do this in 4 dimensions in Euclidean space, if you want to follow it. It's kind of fun. And the reason it's kind of fun is you can see that there's no swindle. Right? It's always nice to see that nobody's swindling you. You're just calculating stuff. Okay. So, did I write it down here? Yes. So I'm going to calculate the Higgs, the fermion, and the Higgs. Exactly the same standard model Lagrangian. And what am I going to get? I'm going to get that this is equal to delta mh squared minus lambda f squared over 8 pi squared, lambda squared. Okay. And I could have guessed this guy too, because why could I have guessed this guy? Aside from the fact you guys know the answer. I could have guessed this guy because there's no symmetry that protects the Higgs mass. There's nothing, no parameter over there that when I set it equal to 0 makes it vanish. So there's no symmetry that says it can't get a dependence on the cutoff, and so it does. Okay. However, scalars are different here. So suppose I say, I want to cancel this guy. So I'm going to add 2 complex scalars. Phi 1, phi 2. Okay. So you guys are thinking in your mind, Susie, right? But these are just 2 complex scalars. And I'm just going to write the simplest Lagrangian I can write. D mu phi 1 squared. There's no half because they're complex. Plus d mu phi 2 squared minus m1 squared phi 1 squared minus m2 squared phi 2 squared. And then I'll just put in a coupling plus lambda s, my Higgs field squared, which I called phi squared. So this is my Higgs field. The same phi is over there, times phi 1 squared plus phi 2 squared. Okay, so now I'm just going to do exactly the same calculation. I'm going to calculate the Higgs, and these 2 phi's, phi 1, and then I'll have the phi 2. And lo and behold, when I calculate this stuff, delta mh squared equals lambda s over 16 pi squared 2 lambda squared, plus some logs. So here you have the motivation for supersymmetry, right? If I pick lambda s equals to minus lambda f squared, did I erase that one? No, here we go. So lambda s equals minus lambda f squared plus lambda f squared. Yeah, they cancel. Okay, that's cool. Scalars cancel. Anybody going to ask me about the diagrams I didn't draw? Because there are other diagrams, right? There's stuff like this. Phi 1, H, 8. There's that kind of stuff, right? Yeah? Yeah? So these guys, I'll just tell you the answer. These guys go like log of lambda. They don't give lambda squareds if you can't calculate them. Okay. So supersymmetry, it cancels these guys. And in general, if I want to cancel these guys, I add extra scalars. So what happens when I actually put in the rest of these pieces? And I didn't write down the factors because they're not so relevant.
The number and this row only is there when once the Higgs gets good, right?
Yes, right. Lambda f. Did I erase the right one? Yeah, lambda f. Yeah. Because the Higgs, right, yeah. This is after electroweak symmetry breaking. So now if you actually want to keep doing this stuff and include the logarithms in these pieces, what you get, let's see, over here, is you get a lambda f squared log mt squared over lambda squared piece. Right, that's just keeping the rest of the terms there, the logarithms. And over here, you're going to get a lambda s times the logarithm of the mass of the scalars, s1, s2. Okay. So once you cancel these quadratic pieces, the logarithms are still there. Okay, and what you're going to get is lambda f squared log mt squared over lambda squared plus lambda, well, we'll call it, I can't remember this, lambda s log, actually I can remember the sign, it's a minus sign, ms squared over lambda squared. So in order to cancel the quadratic pieces, you need mt squared minus ms squared, not too big, shall we say, not too big. Okay. So Matthias pointed out that the unitarity argument for new physics at the TeV scale has now been superseded by the fact that we saw a light Higgs. But this particular argument still remains, that you still have these log lambda squared terms which depend on the difference between the top mass squared and your scalar mass squared. So when I say not too big, that's in the eyes of the beholder, I think. Okay, I'm going to stop here and take questions. Okay, because this is a stopping point. Okay.